Hello everyone and welcome on this video on the topic of temperature profiles you get out of GHEtool Cloud. Temperature profiles are at the very center of borefield design because when you enter all your ground data, your configuration data, your thermal demand within a simulation software, in the end you will end up with some type of temperature profile. And it's important that you are able to interpret these temperature profiles in order to know whether or not your borefield is sized correctly. Today's video will be exactly that, so reading the different temperature profiles you get out of GHEtool Cloud. And there will be another video in the future where we will be more focusing on the physics behind those temperature profiles. So basically how we can get from the inputs to the final results. But let's start with the beginning and just reading those profiles, what we can learn about them. So for today's video we have prepared two scenarios, one with monthly data, so that's related to the thermal demand app, where you can either enter the monthly data or hourly data. So for monthly data we have entered here the relative data with just the peak power in heating, cooling and the yearly energy demand, which is then automatically distributed amongst the different months of the year. If you want to, you can also enter the values directly for every month, but for the purpose of this video we kept it rather easy and chose to work with the relative load. For the hourly data we have imported an hourly profile for a certain building of which we had a dynamic simulation. So we have the heating and cooling load for every hour of the year. So let's start with the monthly data. Before we move over to the results step, I just want to address two important parameters. So whenever we do a geothermal design, we need to make sure that the temperature of our geothermal fluid stays between certain temperature limits. And on the general tab, you can see that we have both a minimum average fluid temperature and a maximum average fluid temperature. So these are very central and important to the design of borefields. The regulation is a little bit different from country to country, but the maximum average fluid temperature has also a technical side to it. Namely, if you want to passively cool your building, which is also called free cooling in some places, the temperature cannot be too high. Because if the temperature you have in the ground is too high, you will no longer be able to cool your buildings in a passive way, meaning without a heat pump. So that's why it's typically in Belgium restricted to 17-16 degrees from this technical point of view. The minimum average fluid temperature has more to do with sustainability reasons. And you do not want to freeze your ground because of all the microbiological life in it. But also when the ground is freezed down, then you will no longer be able to extract heat from it. So it's possible that your system will fail. It's also important to have some type of buffer between the freezing point of 0 degrees Celsius, and that's why I often choose 2 as a minimum temperature. So if you move over to our results tab, we see that for every monthly simulation you do, you have 5 lines. So the 2 dotted lines I already explained, it's the minimum temperature you set and the maximum temperature. So these are constant temperatures. And then you have 3 lines. You have the fluid temperature for the peak heating, for the peak cooling, and you have the borehole wall temperature. Now let's just start with the borehole wall temperature. This is basically the temperature at the interface between your borehole and your grounds. So that's the temperature at which everything starts. And as you can see, typically there is a sort of sinusoidal curve where it heats up over summer and it cools down over winter. That's because in the summer you have the cooling, which you put into the ground, and in the winter you extract the heat from the ground. And the specific looks and feel of this curve, of course, differ from project to project. But this is basically the temperature from which everything starts. Then we can add the red line, which is the fluid temperature during peak heating. So when your heat pump is on, it will inject a temperature that's colder than the borehole wall temperature into the ground in order to extract the heat from it. Now, the temperature you see here, it's the mean average fluid temperature, meaning it's the average between the in and the outlets of the heat pump or the borefield. So, for example, if you have a temperature difference over the borefield of 3 degrees, and you have here a temperature of, let's say, 5 degrees, then you know that the temperature that is going into the borefield is 3.5, and the temperature that's going out of the borefield is 6.5. So it's always important that you know that these temperatures are the average fluid temperature across the in and the outlet. And you can see the same sort of seasonal variation you saw with the borehole wall temperature as well. And then we have also the same type of curve for the peak cooling temperature. So you might be wondering, why is there a difference in heating and cooling? Well, it's because we work with a monthly resolution. So in every month, which you can also see from the thermal demand tab, it's possible to have both heating and cooling. Depending on the type of building you have. For example, if you have an office building, there will be cooling demand for every month. If you have, for example, also a data center or a lot of computers there. So it's very building dependent. But basically in every month you have both heating and cooling, and therefore in every month it's possible to have both a high temperature in cooling and a low temperature for heating. So that's why it's separated when you work with monthly resolution. So that's basically what you can see here. There is also an imbalance, which is also in the numerical results. That's basically that the ground cools down year after year after year. And it says here it's extraction dominated, meaning that we extract more heat from the ground than we inject into it, and that's why the ground cools down year after year. So that's everything related to the monthly temperature profile. If you move over to the hourly data, you see that we have the same temperature limits, but we now have just one fluid temperature and one borehole wall temperature. And that's due to the fact that when we work with an hourly resolution, at every hour there is just either heating or cooling. That's an assumption that's behind it, that is namely that at the time interval of an hour the building will not be cooled and heated at the same time. So it will cancel out on an hourly level, and that's why we only need one temperature here. So the borehole wall temperature, it has the same profile as you can see in the monthly resolution, but let's zoom in a little bit by pressing Ctrl and scroll. You will see that when you zoom in, it's much more spiked because of the higher resolution of input data. So that's the borehole wall temperature, and then we can add the fluid temperature on top, where if you zoom in, you can very clearly also see the different spikes from hour to hour. So here the same thing, the blue lines is the average fluid temperature, so it's the average across the in and the outlet of the borehole. Another curve you always have when working with hourly data is the load duration curve, which is for the heating and the cooling demands. So you can see here that in this case there is way more heating demand than there is cooling, but the peak cooling is way higher, which you can also see on the temperature profile, where there is a large imbalance. The ground cools down year after year rather significantly, of 233 megawatt hours, but the peak in cooling is higher. It also crosses the temperature limits, in this case for I think just 1 or 2 hours. So perhaps you can say, well, we need a slightly bigger bore field, but in this case I think it's rather well designed. So that was everything I wanted to say in this rather short video. There is also an article over on our knowledge base, which explains also what I've been telling you today. If you think this video is interesting for you or for your company, please consider subscribing so you are notified whenever a new video comes out. Perhaps share it with some of your colleagues so they can also learn more about geothermal design and GHEtool Cloud. And I hope I can see you in the next video. Bye.